start with number one, going back and doing some older stuff. I first want to go through what I think might be something helpful, though, as you're studying and as you take the exam. Right? There we go. Excuse me. So we've looked at situations where we are building confidence intervals or doing hypothesis testing for the difference in sample means, but I have known population variances, right? So when I had known population variances, I got to use that z-table or the standard normal distribution. I also had examples where I was looking for the difference between sample proportions. That was a scenario where I also said we can use that standard normal distribution. The issue became when we were looking at things that only have sample variances. So if we looked at the difference between sample means and all we have is a sample variance for both populations, or I'm looking at a sample difference and all I can do is find the variance of that, that sample I had, or we're looking at a coefficient, all we have is this standard error, which is kind of using our sample. These were all situations in which we knew we should be using that student t distribution. Okay. So, this kind of helps, here's our 5 different kind of scenarios. It kind of helps us keep it together. Anytime I see proportions or I have a known population variance, z-table or standard normal distribution. Anytime any other time where I've got sample variances or I'm looking at the sample difference and all I have is a variance and the coefficients, we're going to be using that student t. Okay. So hopefully that kind of helps keep things straight as we dive into these problems. On the formula sheet, I'll also point out the confidence interval equations of the test statistics kind of remind you of this. So when I've got sample means and population variances, I'm using that standard normal or the z-table. When I'm looking at, waiting for the screen to catch up here. When I'm looking at proportions, use that z-table. When I've got sample means but only sample variances, now I have to use that student t distribution. And the test statistics kind of have a similar thing, right? Known variances or proportions, the test statistic is a z-statistic, comes from a standard normal distribution. Anytime I have a difference in means but only sample variances, that's a t-statistic, comes from a student t distribution. Same kind of thing if I'm looking at the sample difference, it comes from a student t distribution down here. I don't know why these look small to me, but I'm going to increase the size here a little bit. Okay. So for this very first problem, we're looking at kind of CEOs. And in 2010, we had a sample of 30 CEOs. We found their average age is 45, variance of 36. In 2016, we took a sample of 25 different CEOs. We find their average age is 50, and they had a variance of 25. So if I tell you, here we've got sample variances, usually we'd have to find our degrees of freedom, right? But this is the one where I said I won't make you use that kind of big complicated formula to get delta or the degrees of freedom. I'll give you an assumed true degrees of freedom. So assume here the degrees of freedom is 40, okay? So the very first question is asking, okay, I want to build a 95% confidence interval. Okay? So if I have a 95% confidence interval, my alpha should be what? Just the area, just the area outside my interval in decimal form, 0.05. Okay? Now, kind of important here we note that we want the difference between 2016 and 2010. Where group 1, right, is that 2016, and then group 2 is 2010, right? And I kind of identify that up here in what I was giving you. So, we've got our alpha. Let's go to our formula sheet as a reminder. Here's our confidence interval equations. Right, which of these do I use? Well, I've got sample means and only sample variances. So I have to use that student t distribution. I've got my alpha, but I need to have alpha over 2, right, on each side. So looking at that student t distribution, I want the t value such that the total area outside of my interval is alpha, which means that there's alpha over 2 on each side, or 0.02 on each side of my confidence interval. okay? Everything else is just a matter of plugging it in. I was given the 2 sample means, I was given 2 sample variances, I was given 2 sample sizes, right? So it's really just a matter of plugging in those values that I was given. So I'll kind of write this out. So we look at the difference between the first, or we'll take, I'll just write this out and then write underneath it. So the first thing we'll do is we'll look at for that sample difference between the 2 groups. So average age in 2016 was 50, average age in 2010 was 45. The next thing we need to do is look up that t-value. So the area I wanted in the tail was 0.025, and my degrees of freedom was told to me to be 46. So I'm going to go to that student t table, right? The area I want in my tail, 0.025, degrees of freedom, 46, 2.013, okay? So why does that not sound right? 2.013, 2.013. Okay. The next part of my equation, first of all, any questions on kind of how I found that value, right? Alpha over 2 is the area 1 in the tail, degrees of freedom of 46. So we go back. Nope, that's the answer key. So then I just need to get this final part, right? So sorry, I was kind of trying to write this out here. So first group sample size, sample variance over its sample size. Second group's sample variance over its sample size. So now it's just a matter of grabbing those from up here. So for group 1, variance is 25, sample size is 25, that's convenient. Variance was 36, sample size was 30 for the second group. So all I've really done there is just plug my values in to that confidence interval equation. And I had to look up that t-value. Any questions on that before we keep moving here? So one thing, before we even kind of got too far into this, we could have done is said, okay, look, this kind of represents my sample difference, right? The difference in my sample means that sample difference I found. Well, here I found a sample difference of 5. I'm building my confidence interval around that. I'm going to go 2.013 standard deviations to the left and to the right. Remember, kind of this guy right here represents that standard deviation between our sample means. So if I know that my confidence interval is centered around the value of 5, if I look at these potential answers, I can rule D out right away, right? 5 is not even in that confidence interval. Now, the other 3 all kind of make sense. 5 is exactly in the middle, so there I have to do the computation. We already have the equation written out. It's just a matter of getting it entered into our calculator. If we do, we should get this value right here, right, for our lower and upper bound. Subtract our margin of error to get the lower bound, add it to get the upper bound. Any questions on that one? I'm going to shut the door real quick. All right. So I'll just shut the door real quick. So the next one is we've got some hypothesis testing. We're given a null and an alternative hypothesis. So what's the test statistic, right? Well, it doesn't really matter what type of tailed test we have. We calculate the test statistic the same way if it's a specific scenario. So here, if I'm thinking about my test statistic, I've only got sample variances. So I go to that formula sheet. Here's my 3 test statistic equations. Difference in sample mean, I only have sample variances, okay? So I'm going to write this down and try to kind of line this up with a little bit with what we were doing with the confidence intervals, and hopefully by the end we'll bring everything together. So I'll take the difference in my sample means, divide by each group's variance over that group's sample size. Kind of notice I have similar components, right? For my confidence interval, I was basing the confidence interval around that sample difference. That's my numerator in the test statistic. and I want to go this many standard deviations away. Well, here I need to divide by the standard deviation for the difference in my sample mean. So you kind of notice there's very similar components in each of these, right? You know, I could plug all my values in here. So what, 50 minus 45 divided by square root of 25 over 25 plus 36 over 30, right? Because it's the same values as I was using for my confidence interval, so it should go pretty quick. So really, these test statistic equations, it's really just a matter of identifying the correct test statistic, and then it's just plugging your values in. Now, to avoid some easy mistakes, or maybe to rule out some answers, notice I've got sample variances and sample sizes down here in my denominator. My denominator will always be positive. For every test statistic, that denominator is always representing a standard deviation. So the standard deviation for the difference in my sample means. The standard deviation for the difference in sample proportions. The standard deviation for the difference in sample means with known population variances. The standard deviation of my sample difference, right? So they're all going to be positive denominators. Okay? So if the denominator is always positive, here, the sample difference that I find tells me what the sign of the test statistic is going to be. If I find a negative sample difference, it's going to be a negative test statistic. If I find a positive sample difference, it's going to be a positive test statistic. Why? Because I'm using that assumed true value, or that assumed true difference of 0. So we're always going to be using that for our examples. So our numerator tells us the sign of the test statistic. So right away, I say, well, look, I found a sample difference of 5. That's my numerator. So when I go to the answers here, I should be able to rule out C right away, right? Because I know that I found a sample difference that was positive. My test statistic should be positive. If I plug all those values in to my calculator here, I should get that 3.37, okay? Any questions on that before we keep moving? Marker's dying a little bit. We'll kind of switch colors here. Okay, so we've got, here I gave you a null alternative. I would have asked you to identify it. Well, if you want to test for whether or not the age of CEOs has increased, right? Well, then when I take 2016 minus 2010, if it's increased, that would be that the difference is positive, right? It's higher in 2016. So I'm testing for whether or not the difference is greater than 0, so I assume the opposite is true. Look at my alternative hypothesis. I have a greater than sign, so I know this is a greater than or a right-tailed test. So when I'm looking up critical values, what I'm going to be doing is I'm using that student t distribution. I've got a right-tailed test, so my critical value is the value that gives me alpha total to the right, right? So what t-value would give me an alpha of, and I'm going to look up alphas of 0.1, 0.05, and 0.01, and I was told, right, we had that assumed true degrees of freedom of 46. Okay? I think it was 46. So I'm going to go here, look up on my student t table. I know that I want the areas of 0.1, 0.05, and 0.01, and I want that at the degrees of freedom of 46. Right? So I'm going to try to get this all on one line here. So 46, so 0.1, that critical value would be 1.3, 0.05, the critical value is 1.679, and at 0.01, the critical value is 2.410. Okay? So I'll blow this up here in a second, but I want to show you, I want to make sure I don't forget all these values. So what we really just did was, so 1.300, 1.679, and 2.4 something, 2.410. We can think about it's a right-tailed test, so our rejection region is the area to the right. And so this is kind of the setup I have for my critical values. Okay. Any questions about how I looked those up in that student t table? So just as a reminder, this corresponded to the 10%, 5%, and 1% significance levels, which, if we think about the confidence levels, would be 90, 95, and 99. Okay? Now, one thing we could have known right away is that, well, look, the student t-distribution is centered around 0. So anytime I have a right-tailed test, my critical values will be positive, left-tailed test negative, two-tailed will have pairs. So when I was looking at those potential answers, even though I looked the values up, I could have ruled out B and D right away, right? I know it's either going to be A or C. We identified that it was, in fact, C. Right? Now, here's where, if I start asking you to make rejection decisions, well, if you got the test statistic wrong, how are you going to get, you might not get the rejection decisions correctly, or if you got the critical values wrong. So I'll show you kind of, in this question, you can do it multiple ways, right? But the next question asks you, okay, assume the test statistic was 2.013. So now I'm giving you an assumed true test statistic. What's the p-value and outcome of the hypothesis test? Now, if you were pretty confident with your critical values, what you could do is say, well, look, if I take this test statistic, so if I'm trying to, 2.013, it's about right here. Test stat. Right? Well, I can see it's in the rejection region at the 90 and 95% level, but not the 99. Okay? So if I'm making a rejection decision, I believe the question is set at the 99% level, I should be failing to reject. But how do I find the p-value? Well, the p-value is the probability that I saw the test statistic I did, or something more extreme that goes against the null, which for a right-tailed test is just something that's above it or to the right. So this kind of red shaded area represents my p-value. How do I find that? I told you on the last exam, when we would deal with these student t-distributions, I wouldn't make you do this, right? And I still won't make you put it in a range per se, but if we're using the student t-table and not Excel or something, I only have, at the degrees of freedom 46, I only have 6 different t-values I can even look up. So my t-value is 2.013. So at degrees of freedom 46, okay, well that's one of those numbers in the table. And that's how I do it on the exam as well. If I give you an assumed true test statistic and I want you to find the p-value, it should be one of the values in this table. Sure enough, here it is. The area to the right, 0.025. So my p-value is 0.025. Right? It's the only one that's 0.025 here, but we already said I also know that I can make that, I failed to reject. Right? So even if I didn't use the critical value approach here, get the paper separate. So if I didn't use the critical value approach, and I'm thinking about, okay, what if I use the p-value? I only reject if the p-value is less than alpha. So my p-value of 0.025, that's less than 0.1, so I reject. It's less than 0.05, so I reject. Not less than 0.01, so I fail to, right? Making the same decisions if I use the critical value approach there. So if it's a short answer and I kind of leave it open-ended, like make your rejection decision, you could use either the p-value or the critical value approach. Okay. Any questions over anything here? Okay. One thing that I do want to point out, because I started grading the other sections, Excel's first, and I've seen this as a common problem. So I want to connect something here. So if I'm looking at my confidence interval, right, basically what that's saying is the true difference, right, is somewhere, the true difference between these sample means is somewhere in between 2 and 8, right? So if I do a hypothesis test for any value in this range, and I'm using that assumed true difference of 0, well, if 0 is not in this range, I should be rejecting the null, right? I should be rejecting that 0 could be the true difference because it's not in my confidence interval. Sure enough, I gave you an assumed true test statistic here, but if we were to use the actual test statistic, right, 3.37, well, that would have been way out here. I definitely would have been rejecting at every level. Right? So, you know, if I do a hypothesis test for any value outside the range of my confidence interval, I should be rejecting the null. Right? I should be rejecting whatever I've assumed that difference to be. Now, if I do a hypothesis test for any value within this range, well, I'm saying the true difference could be these values. So if I assume that the true difference is anywhere between 2 and 8, I would fail to reject those values because those could be potential differences. Right? So kind of lines up here. Now, technically, what I just said really only applies when you're looking at confidence intervals and two-tailed tests, right? Because here I've kind of eliminated one side of the the differences, but here in the confidence interval, I allow it to go in either direction. So it really, that idea only lines up when we're comparing the confidence interval to a two-tailed test, but it'll be pretty close with one-tailed as well. Any questions on that? Okay. So I'm going to skip around a little bit because I think it's probably good if every, today, Friday, and even on Monday, kind of before that exam, to get a little bit of hypothesis testing and a little bit of linear regression kind of every time, right? So scroll down here. We're going to start with, I guess it's question 7, but I'm just kind of going to go through and show you some different stuff with this regression output. So let's say I'm trying to predict GPA, and I've got these 5 different variables. So the SAT score measured in points, athlete variable, which is a 1 if they were an athlete, 0 if not, their high school ranking, female, which is a 1 if they're female, 0 if not, and then the total credit hours taken, factored into this GPA, okay? So I run this regression and I get this output. Right? So the first thing is, how do I do these coefficient interpretations, right? The slope coefficient on SAT, what's the correct interpretation? Well, the interpretation of these slope coefficients is always the same, right? It's the correlate, or if the X variable is 1 unit higher, then the predicted Y value would go up or down by whatever this coefficient value is, right? If it's positive, it increases by this much. If it's negative, it decreases by that much. Holding everything else constant, right? When we include multiple variables here on the right-hand side, we said the interpretation is the same. We just add on this phrase, holding everything else in the regression constant. So right away, if we're looking at these potential answers, we need to have this holding everything else constant there. So I can rule out B right away. Right? So from there, what's a 1 unit change in the SAT score? So 1 more point on the SAT score, right, is correlated with a 0.002 increase in our Y variable or increase in GPA. So that would be A. Right? And that's just using that general form of the interpretation, right? Our slope coefficients don't represent averages. Here, this is a correct interpretation. You just use the wrong coefficient value, right? You use the intercept as opposed to the slope coefficient on SAT. But that's the way we interpret these slope coefficients every single time. A 1 unit increase in the X variable is correlated with or changes the predicted Y value by whatever that coefficient is. Questions on that before we keep moving here? The next question is then, how do we interpret the intercept? So the interpretation of the intercept is always the same. It's if all the X variables equal to 0, the intercept is the predicted value of GPA, the predicted value of your Y variable. So in this case, if every other variable is equal to 0, so someone who has a 0 on the SAT score, not an athlete, ranked 0 in the high school, not female, 0 total credit hours, their predicted GPA would be 0.8. Now, these interpretations of the intercept, I think we went over this a little bit on Monday. They're really weird. Sometimes they make no sense, but that's still how we interpret them because that's still what they represent. They represent that if we could see all these variables be 0 at the same time, this is where that Y value starts. Okay? So for an individual that has not the average SAT score and not the average height, but for an individual that has a 0 SAT score, ranked 0 in their high school, is male, non-athlete, etc., their expected GPA is that 0.8. Okay? So just more slope and intercept interpretations. Now, here's a question where we see this on the exam. I'm hoping that, kind of like when I asked calculated mean in the first exam, everybody should get these correct. If I ask you to find a test statistic for a slope coefficient, in this case on the athlete variable, all it is, right, is you're going to take, sorry, I'm thinking ahead. All you're going to do is take that coefficient estimate and divide it by your standard error. Now, technically, we're subtracting that assumed true slope, but we said for every single slope coefficient, we're always assuming that it's equal to 0. So if this is 0, it doesn't change anything. So to get that test statistic for your slope coefficient, all you do is take that coefficient estimate and divide it by your standard error. So if I'm going up here, notice I didn't give you the test statistics. You would want to take that 0.162, divide it by that 0.04. It's as simple as that. You could technically, you know, if I was doing this in Excel, I could find the test statistics really easy, right? For every single one, it's just take this cell, divide it by this cell, right? Coefficient estimate divided by the standard error. If I do that, right, I can move this ahead. I can double check that I know how to do this, right? Just take the coefficient, divide it by the standard error. That will reproduce all these test statistic values, okay? So if we divide 0.162 by 0.043, we get about 3.75, okay? I'll just move that back for right now. So yeah, we got that about 3.75 there. Okay? But that one should be really easy, right? Just take the coefficient estimate, divide it by the standard error, right? Any questions over any of that before we keep moving here? All right, so what I'm going to do next, well, we'll go through one more just so I can kind of tick it off. But on number 11, and we'll save kind of 10 for next class. On number 11, if I wanted to, like let's say I didn't give you the p-values up here, right? And I wanted you to find the p-value, because if you can calculate the test statistic, well, you can look it up in a student t-distribution. We haven't talked about degrees of freedom because I'm not making you do that. But if you were wanting to look up that p-value, what distribution, what type of tailed test would you use? Well, we said earlier, these slope coefficients, the test statistics are coming from a student t-distribution. And if this is always the null hypothesis, then the alternative hypothesis is always that it's not equal to 0. We're always going to have a two-tailed test. So two-tailed test and student t-distribution, okay? So now we're going to go back up, and I'm going to create some questions. So this is why showing up or watching the Zoom or watching the video after the fact, this is the value. I'm slightly perturbed / worried for all the lack of kind of people on Zoom and kind of here. So so this is a reward for those who showed up. So let's say one thing we'll just get out of the way that you might be asked to interpret, or you might be asked, you know, slightly different questions on is, let's say I asked you, what percent of the variation, so what proportion of the variation in GPA are your X variables explained? Right? So if that's the question that I ask you, what statistic should you be looking at? That's literally the definition of our R squared. Okay? The R squared tells us the proportion of the variation in the Y variable that our X variables explain. Right? So here, you know, the proportion is 0.27, or we can think about we're explaining 27% approximately of the variation in GPA with these 5 variables. Okay? Now, a second question I might ask is, which of the variables are significant at the, let's say, the 10% level. Okay. So when we say a variable is significant, right, or statistically significant, it's really the same thing as saying which ones can you reject the null, or reject the null for. I speak faster when I type, and then so it's really asking what variables are significant is the same as saying which variables can you reject the null for, because if we're rejecting the null, we're rejecting that there's no relationship. And what we're really saying is we reject that there's no relationship because we found evidence that there is a significant relationship, at least at the 10% level. So those two things can be the same thing. If something is significant, that means that you're really rejecting this null. Okay? Well, how do I make rejection decisions? We only reject if that p-value is less than alpha. So our alpha is 0.1 here. So if we look at this output, this one's not overly interesting. Why? Because all these p-values are basically 0, right? All these e to the negatives, that's basically a p-value of 0. So here, you know, I would say that all variables are significant at the 10% level. Okay? Or I reject the null for all of them. Okay? Now, probably on the exam, what's a little bit more realistic of an example for you to see is not something like this. I probably would do something more like, I don't know, 0.345, 0.0739. Change this one, 0.0432 or whatever. Right, maybe something like this, where some of them you wouldn't be, right? So now if I ask that same question, which of the variables are significant or have a significant relationship with GPA, our Y variable, at the 10% level? Well, now the SAT variable and the female variable, we don't reject the null. So if we fail to reject the null, what we're really saying is we fail to reject that there's any significant relationship between GPA and these variables. So if instead I had given you these p-values, you basically would say total credit hours, high school rank, athlete, and if you wanted to, the intercept are all significant at that 10% level. Okay. Any questions? Like, I know I changed the p-values here, but I'm just trying to show you something that's a little bit more where there's a lot more variation, where not every p-value is equal to 0. Right? Another possible question is, let's say I asked you, what is the change in predicted GPA from taking 20 additional credit hours, right? Well, if we go up here, the interpretation of the slope coefficient on credit hours would be for every 1 additional credit hour someone takes, the GPA is correlated with a GPA is correlated with a 0.002 increase in GPA. So if this is the effect of 1 more credit hour, right, 1 unit, the effect of 20 would just be 20 times that, right? Or what, 0.04? So I might ask you the interpretation of a coefficient, but using that interpretation, you can then find the effect of more than just 1 unit, right? Well, how do you do that? Well, the effect of 20 units, and then this is the effect of 1 unit, 20 times that. So the last thing I'm going to add in here, or another question I could ask you, is what is the predicted GPA for a, let's say, male, non-athlete, ranked 30th in their class, SAT of 1100, and taking 40 credit hours. Right? And I'm going to try to get this all in one line for us. I'll just delete these blank lines for right now. So what is that predicted GPA? Well, I basically have this hypothetical person. I have all these coefficients. If I go up here, really this is the equation that I'd be using to make my predictions, right? So One thing that I'll probably add onto that formula sheet and update it this afternoon is I'll throw this equation in there for you just as a reminder. And this next equation, I don't know how much it's going to help because I'll write it out in the general terms. But right, anytime you want to predict y, you're going to take that intercept estimate, take that first slope estimate times whatever that first variable is, add in the second coefficient estimate times the second variable. Do that for all the variables you have there on the right-hand side. So basically, to predict my GPA, I'll go through each variable, take the coefficient, and multiply it by that x value for this hypothetical person, then add them all up. So that's what I'm going to do. So I will take that slope coefficient on the SAT, so 0.002, multiply that by the person got N, 1100. Add to that the slope coefficient on athlete, so 0.162, times, well, I have a non-athlete here, so that would be times 0. Add to that the coefficient on high school rank. Well, actually, that's a negative, so negative, or I'll subtract that 0.003 times, they were 30th in their class, so times 30. Add to that the coefficient on female, 0.86. Well, this individual was male, so we'll multiply by 0. Notice anytime you have these are 0, right? Anything times 0 is 0. So if I didn't want to write these in, I wouldn't have to in practice, but I'm just kind of trying to be, kind of show you, how you would do this no matter if it was a 0 or a 1. And then the last one, I'll add in that coefficient on total credit hours times you're taking 40 credit hours, right? So this is correct. I add all those up, but I forgot one thing, right? The one thing I forgot is the intercept always gets added into my prediction, right? So this intercept value of 0.8, I should really have put that at the very beginning, right? I should have started out with that. So, if we do this math, we get what? 0.002 times 1100 plus 0.002 times 40 minus 0.03 times 30. Should get 2.993, unless I made a mistake doing that real quick in my calculator, but I believe that's what we should end up with. So you can come up with a prediction for this hypothetical person using those coefficients and then just inputting their x values. Now, the one thing that I see a lot of people forget to do here, kind of like I left off to prove a point, it's very easy to forget to add in that intercept. So just always start out with that intercept when you're doing the calculation. Okay? So I'll add this equation onto the that final formula sheet as well. Like I said, I don't really know how much it helps you, but it's just kind of there to remind you of the idea of what you're doing with predictions. Okay. Any questions over kind of